So this is the 9th video of chapter 7. We'll go over the concept check on oxidation reduction reactions. Then we'll see about combustion reactions, which are a special case of oxidation reduction reactions. And we'll start introducing other ways of classifying chemical reactions. So let's go over this concept check. So which of the following are oxidation reduction reactions? And if it is a redox reaction, which element is oxidized and which element is reduced? So we have zinc, the metal, as a solid, plus CuCl2, an aqueous solution, yields zinc chloride, another aqueous solution, plus copper, the metal, as a solid. When we have copper or zinc as metals, as solid, just the symbol of the metal by itself, they are in their natural state and their charge will be a zero charge. The other two are ionic compounds. So you find what ions they are to find the charge on each element. So in copper chloride, we have two chloride with one negative charge each, because the chloride ion has one negative charge, being in group 7A. So we have two negative charges in total, and we need to cancel them with two positive charges. And so the copper will have to carry two positive charges, and the chloride has one negative charge each. In a zinc chloride, it's the same. We have two chlorides with one negative charge each. So that's going to make two negative charges that need to be cancelled by two positive charges on the zinc. So zinc will be a zinc 2+ in this compound. So we see that the zinc becomes, from a zero charge, a 2+ ion. So that means zinc has lost, the metal zinc has lost 2 electrons. So from zinc, we draw an arrow and it becomes the zinc 2+ plus 2 electrons, because those 2 electrons have been removed from the zinc metal. So zinc, the metal, is oxidized in this equation. Let's see, the chloride stay the same from left to right, so they don't change. Their oxidation state is the same. The copper, however, becomes, from a cation 2+, it becomes a zero charge metal. So if we write the half reaction, it's going to be Cu2+ plus 2 electrons gives Cu, because for Cu2+ to become just copper with zero charge, you need to give it back 2 electrons. So the Cu2+ will have gained electrons. So Cu2+ in the CuCl2 is reduced. Notice that when we are deciding which element is oxidized, which element is reduced, it's always the two reactants that you need to specify. You cannot say that about the product, right? Because it's what they become after they have been oxidized and reduced. That's what the products are. So let's look at example B, or B. So we have 2H2 gas plus O2 gas gives 2H2O gas. So it's the hydrogen gas reacting with the oxygen gas to form the water molecule. We see that oxygen and hydrogen are both in their elemental state, so they have a zero charge in their, natural state there in the left side of the arrow. Now in water, we can imagine the water, even though it's a covalent compound, we can imagine that if there were ions, it would be H+ ions and O -2 ions, because H, when it's an ion, it's H+, and oxygen, when it's an ion, it's the oxide ion with 2 negative charges. And we can see that we have 2 H+, 2 positive charges would cancel the 1 negative charge on the oxygen. So we can see that the state of the hydrogen goes from a zero charge to a +1 charge. So we have H becoming H+ plus an electron. So the hydrogen in the H2 gas state has lost electrons to become H plus in the water. So we say that then H2, the gas, is oxidized here. For oxygen, we see that oxygen comes from a zero charge and becomes a -2 ion. So that means it has gained electrons. So it's oxygen plus 2 electrons gives O -2. We have now 2 negative charges on the oxygen. So it gained two electrons. So we say that O2, the oxygen in its natural state, has been reduced. So anyway, when you find which one has been oxidized, typically the other element will be reduced. There's no other way around it, because one has to be oxidized, the other has to be reduced. If you have only two elements on the reactant side, then that's what happens. Let's look at the third example here. HCl, an aqueous solution, plus NaOH, another aqueous solution, react to give water, a liquid, and NaCl in aqueous solution. So HCl, even though it's a molecular compound, we can imagine that the ions in there, and actually it's an acid. HCl is an acid, and acids behave as if they were ionic when they are in aqueous solution, when they are dissolved in water. And so the H is an H plus ion in there, and then the chloride is a Cl minus. In NaOH, this is really an ionic compound because we have sodium, the metal. Na is Na plus. Then H, we always make it an H plus when it's in a compound. And then oxygen would be a O -1. And you can see that if you add all these charges up, it's a neutral compound, right? One plus from Na, another plus from H, that's two positive charges, and they cancel with the two negative charges on the oxygen. So that would be the charge on these. Now on the right side, in water, we've seen above that, in water, we can say that the hydrogen is plus 1, and then the oxygen is like the oxide ion, O -2. We have two hydrogens per formula, and so that's why it cancels out. And then NaCl, another ionic compound. So Na is the metal from group 1A, so it's Na plus. Cl is the halogen and makes the chloride ion Cl minus. So notice how the chloride stays the same from left to right of the arrow. It's Cl minus, and it stays as Cl minus. Hydrogen also stays the same. From H plus in HCl and H plus in NaOH, it stays as H plus in water on the right side. So it's not changing either. Oxygen, it's a -2 on the left side in NaOH, and it stays as -2 in water on the right side. So, and sodium stays +1 on both sides as well. So you can see that there has been no transfer of electrons in this reaction. So this is not an oxidation reduction reaction, right? You cannot determine that electrons have been transferred there. And actually, HCl is an acid, NaOH is a base, and together they react to make water and a salt. That's typical of acid-base reactions. So all atoms keep their charges from left to right. This is not a redox reaction, it's an acid-base reaction instead. So let's look at the last example. 8 irons as solid plus S8 sulfur as a solid, and gives 8 FeS, another solid. So you can see that on the left side, both iron and sulfur are in their natural state. S8 is one form of sulfur. Iron as a metal is just iron, Fe. So they are both in their oxidation states of 0. Then FeS, that's an ionic compound. It's made of a metal and a non-metal. So finding the charges on the ions, we can find the charge. So sulfide is a known ion. It's from group 6A, so 6 minus 8, it's a -2 ion. And then iron is a +2 ion in this case, because it needs to cancel out those two negative charges on the sulfide. So it has to be 2+. So we can see that iron goes from a state of 0 to a state of 2+. So if we write the half reaction, we will see that we need to remove electrons from Fe. So it's going to be Fe becomes Fe2 plus 2 electrons that we have removed from the iron metal, so that it's oxidized. So it's Fe as a solid, as a metal that is oxidized in this reaction. And then S goes from a state of 0 to a state of -2. So this means it has gained electrons, 2 electrons. So from S plus 2 electrons, it gets to a state of S2 minus. It has gained electrons, so S8, the solid, sulfur in its natural state there, has been reduced. So one thing you want to remember is that, when the question is asked which element is reduced, which element is oxidized, there are always reactants. It's one or the other a reactant. It cannot be a product. And then if one is reduced, then the other is oxidized when you have only two elements. And if you have more than two elements, typically the third or fourth elements don't change state. So that's how you should do this. Let's continue with combustion reactions. So combustion reactions are a type of redox reactions. They are a subtype of oxidation reactions. So combustion reactions are characterized by the reaction of a substance with oxygen. It's always oxygen reacting with something else that you have a combustion reactions, and you're forming one or more oxygen containing compounds, including water, often including water. Because the oxygen basically, combines with the other elements of the substance and forms, oxygen containing compounds. Combustion reactions are exothermic. They emit heat. They releases a lot of heat to the outside, and a lot of them are, burning. It's simply burning. So you definitely see a flame, and you feel the heat. And so compound containing carbon and hydrogen, so we call them hydrocarbons, or carbon, hydrogen, or oxygen, will always form carbon dioxide and water upon combustion. So when you are burning, combustion really means burning. When you are burning compounds that contains carbon and hydrogen, or carbon, hydrogen, and oxygen, you will always form carbon dioxide and water. So that's a generic form for the compounds containing only carbon and hydrogen. When they are burned with oxygen, it forms carbon dioxide and water. And even if you have oxygen in the formula that you are combusting here with oxygen, you also form carbon dioxide and water. This is something to remember here. But not all combustion reactions produce carbon dioxide and water. However, they all will involve the reaction of oxygen. So oxygen will always be a reactant. So an example here of a combustion reaction that does not produce hydrogen, that does not produce water and carbon dioxide. For example, the combustion of magnesium. Magnesium, when you burn it with oxygen in the air, you have to, start the reaction with the spark, and it burns to form the magnesium oxide. So you see how oxygen, combines with the magnesium to form an oxygen-containing compound here. So this summarizes all the ways that we have covered here that are ways that you classify chemical reactions. So chemical reactions, we've learned they can be precipitation reactions. Precipitation reactions are driven by the fact that you are forming a solid when you are mixing two aqueous solutions. Acid-base reactions are driven by the fact that you are forming water. The acid reacts with the base to form water and a salt. And acids and bases are always in their aqueous state also there. Gas evolution reactions are also, typically from ionic aqueous solutions. And one of the product is a gas, so it escapes as a gas. And sometimes there is an intermediate product from acid-base reaction, for example, or even a precipitation reaction. And that intermediate product is unstable and decomposes into something else where you have a gas. So many gas evolution reactions are also acid-base reactions. And then there is the oxidation reduction reactions. These are a much larger class. They are driven by the fact that you have a transfer of electron from an element to another. And the combustion reactions are a subtype of oxidation reduction reactions. So all of these ways are, driven by first formation of a solid for precipitation reaction, formation of water for the acid-base reaction, formation of a gas for the gas evolution reaction, and transfer of electrons for the oxidation reduction reactions. That's the forces that drive these reactions. But let's look at other ways of, first let's look at patterns to be able to discern what you have when you have a chemical equation. So patterns to look for. Precipitation reaction. It's when you have two soluble ionic compounds, in solutions that you are mixing together, and you're forming an insoluble product of a solid. So basically, two of the reactant are aqueous, and then one of the product is solid. Acid-base reactions, it's when you have an acid plus a base and it gives a salt plus water. A salt is a general name for ionic compounds, because ionic compounds are typically solid and crystalline, so we call them salts because of that. The acid, so to recognize an acid-base reaction, you want to recognize an acid by the fact that there is an hydrogen in front of its formula. And the base will contain OH minus. So you want to see the H as first in the formula for the acid, and then OH ion in the base formula. The salt that is formed there can be soluble or insoluble depending on the solubility chart. So you may have an insoluble compound, and so it can be at the same time a precipitation reaction than it is an acid-base reaction. Gas evolution reactions, it's when you have two ionic solutions. Again, when you have a solid, ionic compound that are soluble, so two aqueous solutions. When you mix them, there is a gas being formed. So one of the products is a gas, so that will drive this reaction. You need to know the product that can produce gases. If you remember from a previous video, it's H2S. H2CO3 will decompose into H2O and CO2. H2SO3 will decompose into H2O and SO2 gas. And then NH4OH, the ammonium hydroxide, will decompose into water and ammonia. So you need to be aware of these compounds, and that they become that they decompose and become gases. Except for H2S, it doesn't decompose; it's already the gas itself. And then combustion reactions. All combustion reactions are also redox reactions, because a combustion reaction is a subtype of redox reactions. We recognize them because they have oxygen as one of the reactant. And when something that is burned with oxygen is containing carbon and hydrogen, the product will be carbon dioxide and water. And even if that something has carbon, hydrogen, and oxygen, it will still form carbon dioxide and water. So that's combustion reactions. And there are other ways to classify reactions. So let's look at this video to introduce you to that.
There are 5 major classes of chemical reactions. A synthesis reaction occurs when 2 or more substances combine to form a single product. When copper is placed in hot sulfur vapors, copper 2 sulfide is produced. In a decomposition reaction, a compound breaks down into 2 or more simpler substances. When calcium hydroxide is heated, calcium oxide and water vapor are produced. A single displacement reaction occurs when one element takes the place of another in a compound. A heated mixture of powdered iron 3 oxide and powdered aluminum produces molten iron and aluminum oxide. This is called the Thermit reaction. In a double displacement reaction, the positive and negative portions of 2 ionic compounds interchange. Mixing potassium iodide and mercury 1 nitrate produces insoluble mercury 1 iodide. Centrifuging removes the precipitate, leaving potassium nitrate in solution. The solution can be checked for potassium using a flame test. A combustion reaction occurs when a substance rapidly combines with oxygen to form 1 or more oxides and releases energy. Methane mixed with oxygen readily reacts when a spark is provided.